This video is part of the series, What's So Important About the Pythagorean Theorem? And I'm going to show you how the Pythagorean Theorem led to the discovery of radical numbers. Before people became aware of the Pythagorean Theorem, they were aware of whole numbers, counting like 1, 2, 3. They were aware of fractions, but they weren't aware that radical numbers existed. So when they encountered a situation like on this geoboard, if we have this triangle that's 1, this side is 1, and this side is 1, what is the length of the hypotenuse? Well, when we use the Pythagorean theorem, we know that a squared plus b squared, another leg squared, equals the hypotenuse squared, which I'm going to call c. So then 1 squared plus 1 squared equals c squared. So we have 1 plus 1 equals c squared, and 2 equals c squared. So they had a problem, because there's no whole number that when we square it gives us 2. There's no fraction when we square it gives us 2. So that led to this awareness of a whole new set of numbers, which are called radicals. And so they symbolize it as the square root of 2. But what it does, it's so revolutionary, and it made them aware of a whole other set of numbers that previously they weren't aware existed. It's as revolutionary as the microscope that led us to see organisms, cells, microorganisms that were too tiny to see without assistance. And that opened whole new worlds. That's what happened with the Pythagorean theorem, in realizing that there's this whole other group of numbers. So it's very, very powerful. But not only that, but look at, like we have this side c, which now we know is the square root of 2. And if I did another triangle right here, and this is 1, this is 1, and this is also the square root of 2. We can see that together, the way that I drew it, it forms a straight line. And the question is, can we add them together to get 2? Is the square root of 2 plus the square root of 2 equal to 2 square roots of 2? And what we can see here is, if I drop down a perpendicular here and I make one big triangle, now the length of my side is 2, and the height of this side here is 2. Then this gives me 2 squared plus 2 squared equals now my new c squared, which I'll call d squared. And this gives me 4 plus 4 equals d squared. And this gives me 8 equals d squared. And I see that the square root of 8 is d. And that we can simplify as 2 square root of 2 is d, and that shows us that we can add them together when they're along a straight line, because they have the same slope, they have the same slant, and we get that same thing because we're just making basically a bigger triangle. So we can add them together. So not only can we can add radicals together when they have the same base, or the same radicand. But if we have a different one, like a square root of, let's say, 5, if I were to draw in a triangle here, which has, let's say, a length of 2 and a height here of 1, then I see that here I'm going to have 2 squared plus 1 squared, and that's going to give me my, let's call this h this time. And this gives me 4 plus 1 equals h squared. 5 equals h squared, and h is the square root of 5. So this here is the square root of 5, and you see how it doesn't line up. It doesn't make a straight line, so we can't add the square root of 5 with the square root of 2 because the numbers under the radical sign are different. So we can't add those together because they don't make a straight line. But when the radicands are the same, we make a straight line, we can add them together. And we can use the Pythagorean theorem to see the length of irrational numbers. So the square root of 2 forms when anytime we're going to have like the diagonal of a square. And right in here, I can draw one in here. When this is 1, that's going to be the square root of 2. So the diagonal of a square is one of the most common places where we're going to see a radical, and that's going to be the square root of 2. But the whole idea of radicals is brought about because of the Pythagorean theorem. Thank you.